And towards the end of the presentation, we will discuss the two broad categories of speed control of various machines, namely the scalar and vector control techniques. So, beginning with an introduction to electric vehicles, we know that there has been a lot of focus and attention in the areas of EVs and hybrid electric vehicles from the past few years, both nationally and globally, again because of various environmental concerns. Uh, Basically, because of the greenhouse gas emissions that are there by burning these fossil fuels. Government of India has also planned for many incentives and many programs so as to promote the faster growth and adoption of electric vehicles. Now, if we look at the major challenges involved in going for the complete electric vehicles or the hybrid electric vehicles, as far as the automobile sector is concerned, or maybe any other sector is concerned, one of the main reasons, at least more relevant to automobile industry, is the lack of charging infrastructure. Right. So today you can go to any petrol station and very conveniently get your petrol or diesel fuel filled basically if I use an IC engine. But such infrastructure is not really existent if we would like to go for purely battery operated electric vehicle or a hybrid electric vehicle. Because again, the battery takes its own time to charge, to get fully charged. So, and there are of course fast charging uh, technologies that are being in place, but again the health of the battery and the life cycle of the battery may not be guaranteed if we very quickly try to charge your battery. So that is one of the main bottlenecks, I would say. Having the comprehensive evaluation of charging infrastructure is what we would need so as to have these EVs very fastly promoted and adopted. And other challenge, of course, is in the use of power electronics and electrical machines. Because now, if I replace an IC engine with a battery, which is the main source of fuel, we see that there is a lot of scope for power electronics and machines in the case of an electric vehicle. So, initially, if we talk about the scope of power electronics, we know that the battery gives the electricity in the form of DC, but the machines that we use to drive the electric vehicle are AC machines. That is again because of the advantages, relative advantages that AC machines do possess when compared to DC machines. So now to interface a three-phase AC machine to a DC voltage source, which is battery over here, we would need a suitable adapter, a power electronic converter basically, which does this conversion from DC to AC, which is nothing but your inverter. And we need to do this in a more efficient manner so that we land up drawing less amount of energy from the grid or from the battery to deliver the same amount of output. So in order to have very good energy efficiency, we will need to have super efficient power electronic converters, and again with the machines as well. Because if I talk about tank to wheel or well to wheel efficiency, the machine efficiency also will come into picture. So therefore, what kind of machines to be used? Is induction machine a suitable candidate, or a permanent magnet synchronous machine is a suitable candidate? That is again one of the debates going on, especially while we talk about adapting battery operated electric vehicles. And third important aspect is of course the energy storage, because the power density of the energy density or the power density of the battery also matters. Because if that is those figures are much lower, we will end up in having a very big size for the battery, in which case again the range of your electric vehicle would come down, right? Now, last another important thing is also in the thermal management of your electric vehicle, right? In thermal management of various components associated within an electric vehicle environment. For example, if you talk about an inverter, now especially if the power levels are quite higher, if the even if efficiency were close to up to 98-99%, if that can be achieved by having proper modulation and power converter topologies, we may have to dissipate or remove a lot of heat from these converters, so as to make sure that the junction temperature of the power electronic devices that we use is within the recommended operating temperature range. So therefore, it becomes so important to ensure the reliability and proper functionality of various systems involved in an electric vehicle architecture, that the thermal management also is given equal importance. So now, if you look at the classification of electric vehicles, we have mainly three kinds of electric vehicles. One is the pure battery operated electric vehicle, BEV, sometimes also called simply EV. In the case of an electric vehicle, the electric motor is used for propulsion. And again, the architecture of that we already know. We all know we have a battery, a power converter, and the electric motor. Now the problem is it the range becomes again limited, right? Because especially with the power density or the energy density figures that we have for say lithium ion battery, we cannot afford to have a very big battery bank on an electric vehicle, which is again going to limit the driving range unless these levels are going to get boosted to very high values, which could happen if you work with a different material. The driving range for the EVs are going to be limited. Now, another classification is the hybrid electric vehicle. In the case of a hybrid electric vehicle, we have both IC engine and electric motor for propulsion. And again, these hybrid electric vehicles can be classified as series and parallel hybrid electric vehicles, which we would look in the slides to follow. But when we talk about a hybrid electric vehicle, we still have the fuel as the source of energy, and the battery is only there to extend the range to support the IC engine to some extent, right? Depending upon what extent, we again have mild hybrid or strong hybrid variants of the hybrid electric vehicle. Now, the third classification is the plug-in hybrid electric vehicle. The only difference between a plug-in hybrid electric vehicle and a hybrid electric vehicle is that in the case of a plug-in hybrid electric vehicle, we would have the additional option to charge your battery as well, which will not be there in the case of a hybrid electric vehicle. So if we can charge the battery also, that is where it is. That is why it is called as plug-in. Then those vehicles are called plug-in hybrid electric vehicles. Now, so initially, let us look at the classification of the hybrid electric vehicle. As I was mentioning in the previous slide, we have series hybrid electric vehicle and we also have the parallel hybrid electric vehicle. Now, in the case of a series hybrid electric vehicle, as the name suggests, we have an IC engine, basically acting like a turbine, which is connected to a generator, and the generator is connected to a rectifier to give an DC output, and this is connected to the motor through an inverter, and we do also have battery there as a buffer. And since the engine and the motor are connected in series, this architecture is actually called a series hybrid electric vehicle. So in the case of series hybrid electric vehicle, we have the motor that is connected to the wheels through this system of gearbox and the electronic differential, which is together called as mechanical transmission. Now, when we talk about a parallel hybrid electric vehicle, in the case of a parallel hybrid electric vehicle, we have the engine and the battery inverter motor system connected to the mechanical coupling, and through this we send power to the wheels through the mechanical transmission, which again consists of the gearbox and the mechanical differential. So now, since these are connected in parallel, this is actually called as parallel hybrid electric vehicle architecture. Now, in this case, the wheels can be propelled because of both IC engine and the electric motor. So now, having looked at some introduction to EVs and some classification of the electric and hybrid electric vehicles, let us try to understand the different kinds of machines that are very commonly used for EV applications today. So, if we talk about the classification of machines, we do have an induction machine, and we also have permanent magnet synchronous based machines, which are very widely used for EV applications today. So, if we look at an induction machine, the technology the robustness of it, the maturity of it is well known to us from the past many years. The squirrel cage induction machines, especially, are quite attractive because of their rugged nature. The construction is also quite simple. Now, these machines are also not as costlier as compared to the permanent magnet synchronous machine based counterparts. The reason being, we do not use any permanent magnets in the case of an induction machine. And therefore, these machines are very less costly. They are going to be cost effective. But the problem is that these machines are not as efficient as permanent magnet synchronous machines, especially because of the additional rotor copper that we have. The rotor copper loss also will come into picture, and therefore these machines are not going to be very efficient when compared to permanent magnet synchronous machines. That is why the power densities of these machines are also quite lower when compared to permanent magnet synchronous machine. Now, if we look at the permanent magnet synchronous machines, we do use permanent magnets in the rotor structure in these machines, and these machines have very good power density values. But again, these machines are going to be quite costlier. The reason being, the permanent magnets are used, and these tend to be costlier, and therefore permanent magnet machines are usually much costlier when compared to induction machines of the same power rating and IE rating. So that it is for this reason that these permanent magnet synchronous machines and BLDC machines are very quite commonly used for EV applications today when compared to induction machine usage. And in order to sort of trying to combine the advantages present in both these machines, we also have the synchronous reluctance machines, SynRM, which are also being explored for AV applications these days. Now, these machines are attractive in the sense that they do not have the permanent magnets in them. Therefore, they tend to be not much costlier. And at the same time, they also do not have any winding in the rotor, and therefore, we do not have a rotor copper loss in the case of the synchronous reluctance machines, as you would otherwise have in induction machines. So that way, in some sense, the disadvantages present in both the permanent magnet synchronous machines and the induction machines can be alleviated if we go for a synchronous machine. So let us look at some of the manufacturers of EVs and hybrid electric vehicles in the market today. From India, we have Mahindra and Tata Motors, which, especially if I talk about the four-wheeler sector, Tata has Tata Tiago, Tata Nexon. Today we have Tata Punch, Tata Curve. A lot of other EVs also have come into picture, and we do also have Mahindra producing EVs, Mahindra ETO, Mahindra E-Verito, and today I think we have Mahindra V3 and some other models. And Mahindra Electric has been primarily using induction machines in their drivetrain, but Tata Motors have been using permanent magnet synchronous machines. Even internationally, we have Nissan Leaf and Tesla Motors producing these electric vehicles and hybrid electric vehicles. And Tesla Motors, in some of its models, used induction machine, I think in the earlier models, and they have also used permanent magnet synchronous machines. And Tesla Motors has also been using the PM assisted synchronous reluctance machines in its four wheelers. Now, talking about hybrid electric manufacturers, we do have many companies venturing into this business as well. For example, Toyota Prius and Honda Accord and BMW 8 are the manufacturers of the hybrid electric vehicles globally. Now, with that intro to machines, in the coming few slides, let us try to understand the speed control strategies for induction machine. Right? Let us try to understand the various speed control techniques, and let us also try to understand their comparative advantages and disadvantages. And towards the end, we'll be in a position to make a comment on the widely used speed control techniques for EV applications. So, in the slide over here is the well-known equivalent circuit of induction machine. So basically, figure A shows the equivalent circuit with both the stator and rotor. And if we refer to the rotor side of it and to the stator side, we have the following equivalent circuit referred to the stator side for induction machine, which is shown in figure C basically. The various electrical parameters are denoted here, namely RS, L sigma S, L sigma R, RR, and M, which represent the stator resistance, the stator leakage inductance, rotor resistance, rotor leakage inductance, and the mutual inductance. So, if we look at the expression for the rotor current, it can be given as EB upon square root RR by S whole square plus omega S L sigma R whole square. And therefore, the air gap power developed, which is 3 times IR square RR by S, can be obtained as shown over here. Now, from this expression, we can get an expression for the electromagnetic torque developed in the machine, which is power upon synchronous speed. And we can see that the torque can be approximately written as, provided we make certain assumptions, especially neglecting the stator drop, it can be shown to be proportional to EB by omega S whole square multiplied by omega slip by RR. Now, starting with simple stator voltage control, meaning I do not control anything related to the frequency of the voltages that is applied to the machine. What I control is only the amplitude of the voltages to be fed onto the machine. If we do that, and as I try to vary the speed of a machine just by varying the amplitude of stator voltage, we see that the curves will appear in this fashion. Lower the voltage, amplitude of voltage that you apply, below would be the torque speed characteristics of the induction machine on the torque speeds plane. So therefore, we can say that if I just rely on simple stator voltage control, the torque generating capability of the machine is going to be reduced. That means if I would want to start much heavier loads, we'll not be able to do that. So therefore, what we can do is, instead of just varying the amplitude of stator voltage, we can change both the amplitude and frequency of the stator voltage so that the ratio is kept constant. So therefore, from the torque equation that we have seen in the previous slide, which is 3 times EB by omega S whole square omega slip by RR, if I keep that ratio constant, then we can say that the maximum torque generating capability of the machine need not be compromised, right? So this ratio EB by omega S is actually your air gap flux completely. So such control schemes wherein we play also with the frequency of the stator voltage apart from the amplitude of the stator voltage are actually called as variable frequency drives, variable frequency control schemes, and are also constant flux control schemes. So that way, these variable frequency control schemes, which we very commonly call today as VFDs, variable frequency drives, which are capable of doing these variable frequency control schemes, can be categorized as VF and vector control schemes, namely the scalar control and field oriented control schemes. So in the coming few slides, let us try to understand these two control schemes and comment on their relative advantages and disadvantages. So initially, if we talk about a scalar control scheme, the scalar control scheme, as I said in the previous slide, is basically a constant flux control scheme, right? And we have seen that the amplitude of air gap flux linkage is going to be proportional to EB by F, where EB is your back EMF. And this is something that one cannot physically access. We cannot physically access the back EMF. So therefore, what we do is, instead of keeping E by F in the machine constant, we keep V by F, where V stands for the terminal voltage in the machine constant. So therefore, this control gets its name as V by F control and not E by F control. So scalar control is also called as V by F control. Now the problem with this is that we have made an assumption over here. Basically, we assume that the terminal voltage is almost equal to the back EMF. which is true only if you are talking about fairly higher amplitudes of voltages. So if we talk about the low speed region, which is when the voltage applied is also lower in amplitude because V by F is constant, we can say that V and E are not the same, right? And therefore, this approximation that V is approximately equal to E does not hold good for lower values of voltages and hence for lower values of speed. Uh, and therefore, we would see that the flux is going to actually decrease at lower speeds. So to alleviate this problem, what people typically do is that you provide a small amount of boost at lower frequencies to your V by F profile so as to compensate for this additional stator resistance and leakage inductance drop. So this is how the V by F profile will look like for a typical scalar controlled motor drive. And FB here stands for the base frequency, and if we operate the machine at frequency lower than the base frequency, we have to keep the ratio of V by F to constant, right? And therefore we see that Vs almost varies linearly with F for all frequencies lower than the base frequency. FB is basically your rated frequency or the rated speed or the nominal speed or the base speed of your machine. Now, at lower values of frequency, we will provide a small boost in the voltage as discussed in the previous slide, so as to compensate for that additional stator drop. And the moment you hit speeds greater than the base speed, we would see that we will not be able to increase the voltage also proportionately, right? The reason being it hits the voltage rating of the machine and we are not allowed to operate it beyond that. So what we can do is in order to further achieve the speed control over speeds greater than the base speed, we can keep the amplitude of voltage kept keep the amplitude of the voltage constant at its rated value and increase only the frequency. Now in the process, if I increase only the frequency while keeping the voltage constant, we would see that the ratio V by F will come down, and therefore the flux, which is the measure of the ratio of V by F, will actually come down in the machine, and therefore this region is actually called as field weakening region. So the block diagram of a typical scalar control looks like this. We have an induction machine which is fed from an inverter. This inverter needs a DC source which can come from the rectifier, and the control algorithm is basically this. We have a synchronous speed set speed omega s, which is passed on to a V by F profile to get V in, and I'll integrate the synchronous speed to get rho. Once I have V and rho, I can get V cos rho and V sin rho, which are alpha beta components of the voltage and angle. Now these two can be transformed to three-phase quantities using alpha beta to ABC transformations, and depending upon the set speed, the control algorithm would apply the right amplitude of the voltages, which will again be converted to PWM pulses to all the six switches present in a two-level inverter by comparing with appropriate triangular carriers. Now here are some of the transient results of the V by F control or the scalar control when the speed ramp up from 10 hertz to 45 hertz is performed. So we can see from the simulation result, when a speed ramp from 10 hertz to 45 hertz is there, the phase current is seen to rise during the acceleration period. The reason being, we will need that additional j d omega by dt during the transient portion, which means there will be more torque demanded, and therefore your phase current is seen to rise to that value. And the modulating signal, we can see that is varied linearly in proportion to uh, your frequency command, because V by F ratio is kept constant. And we can even conclude it for the experimental results. Even the experimental results shown on to the right uh, do tend to match with the simulation results that we have on the left. Now this is another experiment where the machine was running at certain speed, and then the machine is suddenly loaded. We can see that when the machine is loaded, the phase current is suddenly rising so as to meet the additional torque demand. Now, having looked at the operation of the VYF control scheme, let us try to understand the advantages of disadvantages of the VYF control scheme, also called as scalar control scheme. One advantage is that the scalar control scheme is quite simpler. It is very easier to implement because we have just looked at the control scheme. It is so simple. So that way, implementing this control scheme is going to be much simpler and easier. And since there are not going to be any additional sensors, the scalar control technique is also seen to be much cost effective because we don't have to invest in the additional cost of the current sensors in the case of scalar control scheme. And regarding the robustness aspects, the scalar control is also quite robust because it is really insensitive to the variation in the machine parameters to a large extent. Now, what about the disadvantages of scalar control? One disadvantage is basically in the assumption that we made on the first slide when we talked about VYF control. We have seen that the stator resistance drop basically dominates at lower frequencies, and the motor currents also will be seen to rise to very high values at lower speeds. And third thing is that the dynamic performance, which basically is the torque transient response to some step changes in the load torque, is very poor in the case of scalar control of induction machine. That is because there exists some natural coupling between torque and flux in the case of scalar control of induction machine. Now, we will try to address some of the problems that are listed in the scalar control scheme, especially in terms of the improved torque dynamic response using vector control scheme. Now, as we have just seen in the previous slide, when we were concluding the scalar control operation of induction motor drive, that there exists some natural coupling between torque and flux in the case of uh, scalar control or in the case of induction machine in general. Now, if this were the case, if we were to change the torque in the machine, firstly the flux has to change, current has to change, the product of these has to change. And flux, the time constant of flux is usually much higher when compared to the time constant of the current. And therefore, the torque transient response is going to be much sluggish in the case of an induction machine because of this coupling between present between flux and torque. But this is not the case in the case of a DC machine. For example, if I talk about a separately excited DC machine, I can control field current to control flux in the machine, and I can also control the armature current to control the torque in a machine. So that way, torque and flux can be independently controlled if I talk about a separately excited DC machine, which is not possible in the case of an AC induction machine. And vector control exactly achieves this. So one of the major advantages of the control scheme, also called as field oriented control scheme, we will look at in the coming slides as to why it is also called as field oriented control, is that we will be able to achieve much faster dynamics in the torque when we apply field oriented control techniques. So one thing is, if we were to achieve the faster dynamics in the torque, we must have the flux decoupled from the torque, meaning we have to control torque and flux independently. Now, to do this, let us look at the equation for the torque in the DQ frame. By DQ frame, I mean the synchronously rotating reference frame. And I guess you already know the concept of the synchronously rotating reference frame, in which frame the AC variables would look as DC to us, and the control becomes much easier. So, looking at the equation of the torque in the previous slide, we can say that if I keep psi RQ 0, so if psi RQ is kept 0 in this torque equation, sorry, in this torque equation, we can say that the torque becomes proportional to only psi RD and ISQ. And if I keep my psi RD constant, torque becomes only proportional to ISQ, meaning that the dynamics of the torque are now enhanced. Because torque is now being proportional to only ISQ, psi RD is kept constant and psi RQ is kept 0. So if I do that, we as discussed in the previous slide, torque becomes directly proportional to ISQ because psi RD is kept constant. Now, because we are keeping psi RQ 0, what does it mean? It means that the D axis of the synchronously rotating reference frame is aligned along the rotor flux axis. We achieve much better transient response with torque, and therefore this technique is also called as field oriented control. And if I orient my d-axis along the rotor field, it is called rotor field oriented control. If I do orient my d-axis along the stator flux, it is called stator field oriented control. And if I orient d-axis along the air gap flux, it is called air gap field oriented control techniques. So that is where we have all these three classifications of field oriented control techniques. But among these three control techniques, rotor field oriented control technique is what is very commonly used because of its simplicity and some other advantages encountered with the rotor field oriented control technique. So now, if we do this, if I make psi RQ 0 and psi RD constant, we can say that the torque is going to be dependent on ISQ. And this psi RD, which is now the flux, the rotor flux in the machine, can be seen to be proportional to ISD in steady state. Basically, if you work out from the DQ model of an induction machine, one can very well prove that. We can say that the torque is the flux is going to be proportional to ISD. So that way, ISD and ISQ, which are the orthogonal components of stator current, are now responsible for flux and torque in a machine respectively. Therefore, I can say that I can independently control flux and torque in a machine the moment we go for field-oriented control technique, which is very similar to a DC machine having decoupled control of torque and flux by controlling the armature current and field current respectively. So this is the block diagram of the vector control technique of an induction machine. Again, we have the PWM inverter coupled to an induction machine. Now all this is the control scheme. Firstly, I will sense the uh, shaft speed of a machine using a shaft encoder. So therefore, I have a speed feedback. This speed feedback is compared against the speed reference to generate an error. The error is passed down to a PI controller to generate a torque reference. Here the torque reference is ISQ reference. ISQ reference is compared with ISQ feedback, and the error is passed down to a PI controller. Now, at the output of PA controller, we have a voltage. We add the appropriate feed forward term to have VSQ. Similarly, I have an IMR reference, which basically represents the flux levels in the machine. IMR is almost same as ISD in steady state. In fact, IMR is the filtered version of ISD. When you pass ISD through a low pass filter of a time constant tau r, which is the rotor time constant, we get IMR. So IMR is compared with IMR reference, and the error is passed on to a PI controller, and we do have a feed forward term over here. After that, we have VSD. Now I have VSD and VSQ. They can be conformed to they can be transformed to V alpha V beta by having DQ to alpha beta frame transformations, and V alpha V beta can be transformed to VA VB VC by through alpha beta to ABC transformations. Once I have three-phase modulating signals, they will be compared with appropriate triangular carriers to give the PWM to the switches present in your inverter configuration. Now, this frame transformation block alpha beta to DQ would require some angle called as rho, right? Let us try to focus on how one can arrive at this angle rho. Now, we would also need this rho information while transforming IS alpha, IS beta to ISD, ISQ, right? Because we are sensing three currents, IA, IB, IC, and these three currents, IA, IB, IC, can be transformed to I alpha, I beta through ABC to alpha beta transformations, and I alpha, I beta can be converted to ID, IQ through alpha beta to EQ transformations. Now, these ID and IQ have to go to the respective feedback positions corresponding to Q1 D axis stator current loops. So this rho basically, which is the integration of a synchronous speed, can be obtained by adding the feedback which is sensed through a shaft encoder with a slip speed. Now, how do I get slip speed? Slip speed again can be worked out from the mathematical models of the induction machine, can be worked out to be ISQ by tau r IMR, where tau r is the rotor time constant of the machine. So once I have slip speed added to the feedback speed of the induction machine, you have a synchronous speed, which when integrated will give you rho. Now, one obvious disadvantage we can see from the field-oriented control scheme is that we have rotor time constant over here. This rotor time constant is a function of LRR and RR, which are nothing but the rotor self-inductance and the rotor resistance. Meaning, if we cannot estimate these parameters accurately, we would go wrong in estimation of slip. Similarly, if even if we estimate these parameters accurately, if say due to some changes in operating conditions, if say the temperature is changing or due to some nonlinear effects of the BH curve, the inductance values are changing, we can say that these parameters are going to change, but what we have estimated tower is not changing, is not adapting to that, and therefore would again have problem with the wrong values of slip, and therefore it will give you an erroneous value for alpha rho, meaning the decoupling, the perfect decoupling between torque and flux is going to be lost with the field oriented control techniques or vector control techniques. That is why these control techniques are sensitive to the variation in machine parameters. So if in this slide we present the simulation results and experimental results for the vector control of induction machine. To the left, we have the simulation results where speed is ramped from 10 hertz to 45 hertz. And during this acceleration period, we can see that the phase current is rising during the acceleration period. And again, during this period, only ISQ, which is responsible for the torque producing component in the stator current, is changing, while ISD is remaining constant because there is decoupling between torque and flux here. Similarly, we can see from the experimental results that the stator current is seen to rise. Again, the experimental results closely match with that of simulation results. Now, what about the advantages of vector control scheme? One thing we can see from the previous slide is that we have achieved a perfect decoupling between torque and flux in the case of vector control of induction machine, because even during the acceleration period, ISD, which is responsible for flux in the machine, is constant, while only ISQ is changing, right? So therefore, there is decoupling between torque and flux in the case of vector control of induction machine, and therefore the torque dynamic performance can be much improved because torque has to now no longer depend upon flux in the machine. So that is one of the major advantages of vector control scheme. And what is the second advantage? We can see that the motor currents stay in limits even at low speeds. It can be confirmed from this result over here. We can see that the phase current rise is not so much as compared to the resulting V by F control. For example, if I go to V by F control scheme, we can see that the phase current has risen to very high values during the acceleration period, which is not happening in vector control scheme. The reason being, because this I stator current amplitude is square root of ISD square plus ISQ square, and since ISD is kept constant and ISQ is also remaining at a constant value during acceleration period, the reason being when we have constant J d omega by dt, we can say that the phase current is also settling at that constant value. So that way, the rise in the stator current can actually be controlled, or is actually a function of that slope of omega d omega by dt, and it also depends upon the value to which ISQ settles. So that way, we can say that using vector control schemes, inverters can be much lower current rated than compared to scalar control techniques. So these are the two major advantages present with vector control techniques. Now, talking about the disadvantages of the vector control techniques, one thing is that this vector control technique is a complex control. It is so complex to implement that can be very easily understood by looking at the control block diagram. For example, if I look at this control block diagram, vector control technique needs a speed sensor for the closed loop speed control. It also needs current sensors, IA, IB, and IC, to implement the current control. And this method also has a lot of transformations going on over here, and this is going to be more complex than compared to a simple V by F control scheme. We can look at the simplest V by F control scheme where the control structure is so simple, it's not at all complicated, and it doesn't have additional current sensors. And other disadvantage with the vector control technique is that this control technique is highly dependent on machine parameters. As I said in the previous slide, that the vector control technique is dependent upon the rotor time constant, which is the ratio of the rotor self-inductance to the rotor resistance. Again, rotor self-inductance is nothing but the summation of the rotor leakage inductance and the mutual inductance. So therefore, if these parameters are not accurately estimated, estimating these parameters accurately is also a challenge, right? So if these parameters are not accurately estimated, we can say that the performance or the decoupling between torque and flux is not going to be guaranteed. So that way, these control techniques are going to be very highly dependent on the machine parameters, which is not the case in the case of V by F control scheme. Because we can see that in the case of V by F control scheme, in few slides, if we can go back a few slides, we can see that there is no dependence of any of the parameters on this control scheme, right? Now, that is another disadvantage of the vector control scheme. And third disadvantage is regarding the disorientation, right? Because the control scheme that we have established basically assumes that your d axis of the synchronously rotating reference frame is aligned along the rotor flux axis. Now, that is true as long as we are able to estimate the synchronous speed correctly and we are able to output the correct value of rho required for alpha beta to dq and dq to alpha beta transformations. However, if there is field disorientation, then the value of rho is no longer correct. It means that the field orientation is no longer proper. It means again there is going to be, to that extent, the decoupling present between the torque and flux in the case of an induction machine. So these are all the major disadvantages present with the vector control scheme. But however, today if you talk about an industry, vector control techniques are the ones that are very highly used for EV applications because it has inherent nature to decouple torque and flux in the machine, and it also has the current control. So that way, since I always have the current control, I can always keep the currents in the inverters coming out from the inverters to a rated value, and therefore we can make sure that nothing goes wrong in the operation of the machine as far as vector control technique is concerned. So in this slide, we provide a comparison between the scalar control and vector control techniques for the speed reversal. So first, to the left is the scalar control and to the right is the vector control. When the speed is reversed from negative rated speed to the positive rated speed, we see that in the case of V by F control scheme, both ISD and ISQ are changing. The reason for this is because that there is no decoupling present between torque and flux in the case of scalar control of induction machine. But on the right side, if you see, clearly one can see that ISD is remaining constant while ISQ is only is changing during the acceleration period. Meaning there's a clear decoupling between torque and flux present in the case of vector control of induction machine. And another important observation one can make is that the current is staying in a common band during the acceleration period with vector control technique, but the currents are seen to rise to much higher values in the case of scalar control of induction machine. So therefore, we can say that as far as the torque transient response is concerned, as far as the decoupling between torque and flux is concerned, vector control techniques do achieve that, whereas scalar control techniques have inferior torque response characteristics and therefore are not capable of decoupling torque and flux. So yeah, that's all from my side. If you have any queries, I'll be happy to answer them. Any questions from the audience? Okay, I think if you have no questions, uh, thank you all. If you have any questions, I am happy to take that. Otherwise, thank you all for this opportunity. Have another meeting at 3 p.m. now. So,
So, any question from any participants, please? Uh, what's the research is happening in this area? One question in chat box, sir.
okay, sorry, what was the question?
What is the research happening in this area? It is in
Yeah,
chat
so
box.
okay. So if you look at the EVs, the applications of EVs, the research is again in terms of the uh, design of a new machine, right? For example, as I was mentioning, permanent magnets have their own advantages and disadvantages. Induction machines have their own advantages and disadvantages. Induction machines are less efficient, but they are less costlier. Permanent magnets are more efficient and more costlier. Can we come up with a machine that is less costlier and more efficient? That is where the direction of research is. And how do you control these techniques? How do I how optimize the design of these machines is one of the research, yeah, areas that people are focusing on.
Okay, so any other question,
So
please?
how can I
Uh,
implement Clark and Park transformation in discrete environments? So if you use any microprocessor or a microcontroller, you can always because the Clark and Park transformations essentially involves the multiplication of sine and cosine with ISDs and ISQ, right? So you can have there will be some inbuilt sine waves generated in most of the microprocessors. You just multiply them and get ISD and ISQ maybe from IS alpha and IS beta. So that way you can very easily implement these transformations, alpha beta to DQ or DQ to alpha beta transformations using any digital platform.
any other query? So, I think there is no further query. Okay, so thank you very much, sir, for enlightening us with this wonderful session.
Yeah.
Where you elaborated the various drives. Basically, first you elaborated that what are the different kind of EVs, then what are the power converters being used, then basically drives,
Yes.
then which drive is important, or what is the like performance variation in different cases,
Yes.
and vector control you have discussed in detail. So all those areas, vector control, torque control, all those areas are very important when one is going into details of these drives. And as you mentioned that most people focus on the power converter, that they should be efficient, but yeah, efficiency of entire system depends upon every component, which includes drives also. So there is a lot of scope for improving efficiency, and especially cost and this performance both should be optimized. Then our electric vehicle will be, uh, convenient to buy for every person. So thank you so much, sir. Despite you have quite busy schedule, you took out some time and delivered this talk. Thank you very much, sir. We will.
Thank you, Professor Manmohan, and
Thank you,
thank you
sir.
all.
Thank you. Thank you. Okay, so we will take 5 minutes break, maybe 3 4 minutes break, and I'll continue the session because sir was earlier supposed to deliver this entire talk 2 to 4, but he today have some emergency meeting 3 to 4 at IIT Bombay, so he had to finish this early. Now I'll continue this talk, whatever discussion we had happened in morning. So please have a break for 3 4 minutes. We will be back again. Okay, so we start now. Good afternoon, everyone, once again. So, share my board. Hmm. Is it visible? Board is visible to you?
Yes, sir, it is visible.
Yeah, is this visible?
Yes, ma'am. Yes, sir.
Okay, fine. So, this is visible, and I hope I'm audible as well. So, in morning, we have discussed the design of a buck converter. Now, let us move to design of boost converter, DC to DC boost converter. So, we all know that boost converter we need. mm, when we need output voltage greater than the input voltage. So output voltage is greater than the input voltage, and for this is the boost converter circuit we have. So here this inductor, now it is connected to the source, right? And diode is connected at this part to the load. So here we will have continuous current at input side and discontinuous current at the load side. So as we have already said that wherever we are doing the steady state analysis of any converter, then we have certain assumptions like steady state conditions exist that we assume. Second, we are assuming that this is working in CCM, continuous current conduction mode. Then switch is on for a period of d into t, where d is duty cycle. It is off for 1 minus dt. Then it is CCM we have already considered, and capacitor is very large, so that the output voltage is can be considered as constant, and we can use SRA, small ripple approximation, and all components are ideal. So right now we are considering all components to be ideal, and then we are deriving the things, right? We will see if components are not ideal, then how does it impacts? Because this boost converter is, I said previously also, that it appears that it will provide infinite gain. Whatever voltage, input voltage, if you give 1 volt, you can get 1000 volt, 1 to 1000. Ideally it is possible, we will see, but practically it is not possible, that also we will see. So let us see how these things works. So when switch is on, mode 1, so the mode 1 is switch is on, that is for a period 0 to dt. And mode 2, it operates in two modes. So mode 2 is when switch is off, that is dt to t. Okay, so when switch is on, this is the switch, this is on. So if this switch is on, then you will see that this is positive, this is negative, and this is our inductor current. So voltage polarity will be positive, negative. Similarly, this is the polarity of capacitor voltage, so same will be the polarity of output voltage, and this is the direction of current that we assume in very first instance when we do analysis for any converter. Right now, when switch is on, this you can see here, when switch is on at this point, then what happens? This switch is closed, so this is the equivalent circuit. Now if this switch is closed, then this is our diode. Here we had diode, right? Here we had diode. Now what is the voltage appearing across this anode and cathode? This negative terminal will be here, this positive terminal will be here. So across this anode cathode, there will be voltage which is minus V node, and this is the negative voltage. So it will make this diode to be reverse biased. So this diode will be ultimately off. Now this diode is off, so it will look like this. Okay, the circuit will look like this. Now diode is off, so this supply or the source is feeding power to the inductor, and inductor is storing the energy, Now what about the capacitor? We are assuming that circuit is in steady state. Now this is the load, and this capacitor is the alone thing here. So whatever energy is stored in the capacitor, that energy will be fed to, let's this I node, that energy will be fed to this load. So if I write the equation, then what is the VL, which is the inductor voltage? It is equal to Vs, which is the input, right? And this is equal to L di by dt. So I can get L di by dt equal to Vs upon L. And Vs is always positive, L is always positive. So this value will always be positive. It means di by dt when switch is on is positive. So we can see simply this here. This inductor current is increasing when switch is on, right? This inductor current is increasing when switch is on. Now at time t equal to dt, we because this is self-commutating device, so by giving pulses you can turn it on, by withdrawing the pulses you can turn it off. So we have turned it off at t equal to dt. So when switch is turned off, now this switch is turned off, now switch is off, but this inductor current, if you see here, this inductor current has certain positive value. Now this inductor current cannot be suddenly zero, that we all know. That is a property of inductor. It cannot allow the current to drop zero suddenly, right? Now what will be done if this current is not allowed to drop suddenly zero? Then definitely this will try to decrease, and if it is trying to decrease, then this di by dt, that will become negative, and a reverse polarity will be developed over here. This becomes negative, this becomes positive. Now this negative positive, it makes this diode to be forward bias, and the current finds a alternative path which is now blocked through the switch, through this diode, and this diode becomes on, and this is the equivalent circuit. Now once diode becomes on, it becomes forward bias. This is the equivalent circuit. Now in this case, equivalent circuit, if I write the equation, so okay, so in this case, if I write one more equation, that is the IC, let's say when switch is on, then IC is equal to minus I node, because there is no current through the diode. So this IC is equal to minus I node. But in this case, what is the IC? IC is IL minus I node. And what about VL? Because VL is equal to, once we have decided the polarity of VL, that will remain fixed. So this VL is equal to VS minus V node, VL minus V node, which is equal to L di by dt. So now di by dt is equal to VS minus V node upon L. Later on we will come to know that this is a boost converter where output voltage is greater than the input voltage. So Vs is lesser, V node is more. So this term is negative in numerator, L is positive in denominator. So overall this term is negative, and that should be there. If this is not the case, then our converter will never reach to steady state and it will become unstable. It is of no use, right? Current will keep on increasing. If DIL upon GT is always positive in on mode as well as in off mode, then current through the inductor will be increasing only. So after certain time it will saturate, right? So that we do not want. We want the current through the inductor should rise. It should store the energy, then release, store, release, like that it should happen for a converter to operate normally, right? So now this is the negative slope. Negative slope means current will decrease. Current is going like that. Now after t equal to t, again the cycle will repeat. You make the switch on. So now this current was flowing through this diode. Now you have made the switch on. If you made the switch on, this diode becomes reverse bias. So again this circuit will work like that. It will happen. So this is our other equation. This is the this is the first equation. Now previously we have seen two ways. One way was that the average inductor current in a steady state, the average inductor voltage should be zero. That was the one way we have seen. Another way was that volt second balance should be there. Now we are seeing the third way to analysis a converter in steady state. The third way is that what we do, this change we will see. If this converter reaches to steady state, then from 0 to dt, whatever change in the current, that should be the same when it is reaching from dt to t. So this change in current magnitude, I'm talking about the magnitude. So this change in current during on time and off time, that should be same. If it is the same, then also we can say that steady state is reached. So we will find what is the del IL closed or del IL on. When switch is on, then what is the del IL? So we will find this from here. So from this equation which we have just found, we can write this del IL upon GT equal to Vs upon L, right? And what is the dt for here? If I go from this point to this point, dt is equal to d into t, capital D into capital T. So what is the value of IL closed? Vs upon L into this capital D into capital T. So this is the value of inductor current when switch is on. Similarly, if I want to find the value of inductor change in inductor current during off, then I will make use of this equation, right? So del IL upon del T, del IL upon del T equal to IL, del IL. What is del T in this period? Off period. This is the del T in this period, which is 1 minus d into t. So I've written 1 minus dt here equal to same equation I've taken here. So when del IL open, so or you can say switch is off, del IL off or del IL open. What is that? Vs minus V naught 1 minus d t upon L. So another equation is this one. Now we have taken this del IL off with its sign. We have not taken its magnitude. So if you see, this value will be negative only. This value will be negative. So there is two way. One way is that if you take the magnitude, then the magnitude of del IL on or op closed should be equal to magnitude of del IL off. If you are taking magnitude, if you are not taking magnitude, then this equation should remain valid. Del IL closed plus del IL open, or del IL on plus del IL off, that should be 0. Let us put it here. So if we put it here, then this equation Vs dl dt upon L, then plus this equation, that should be 0. And from this we will, if we simplify, we find this V naught equal to Vs upon 1 minus d. So that is the another way to do the analysis of same. If we try volt second equation, let's see volt second equation, then what does it give? So this is the inductor voltage when switch is on. We can see from here also Vs. So Vs into dt plus this is the voltage when switch is off. So that is Vs minus V naught. For how much time it is there? For how much time this Vs minus V naught is there? 1 minus d into t, that should be 0. And if we simplify this, this is d into Vs plus Vs 1 minus d minus V naught 1 minus d equal to 0. So from here also V naught comes out to be Vs upon 1 minus d, and this is the same, right? Now if I know that value of d is between 0 to 1, right? So if I put d equal to 0, then this V output is same as V input or Vs. If I put d equal to, let's say, 0.5, then V output is twice of Vs. If I put d equal to, let's say, 0.8, then this is V naught is 1 upon this. So this is 5 times Vs. Similarly, if I put d equal to, let's say, 0.9, then V output is 10 times Vs. If I say d equal to 0.999, then V output is 100 times, right? If I say 0.999, then it is 1000 times. Like that, if you keep on increase 0.999, then 10,000 times. So what it says, d goes to 1, then V naught should go to infinite. That is the conclusion from this, right? This particular equation, when we are assuming that this circuit is ideal one, right? But this is not always true. We will see it today itself, right? This is not true. So let us consider that this is the output voltage for now. Now average inductor current. So this is our circuit. Okay, before that, I just explain what are the other things. Yeah. So this is our inductor voltage waveforms. This is our inductor current waveforms. Now, what about the capacitor voltage or capacitor or output voltage or capacitor current? So we see that when switch is on, then current, this capacitor current whose original direction assumed is this one. Now diode current is 0, it is not there. So IC will be equal to minus I node. So we can see here IC is equal to minus I node, which is also equal to minus V node upon R. Okay. Now when switch is off, then what is the IC? IC is IL minus I node, IL minus I node. So this is your IL. If I subtract minus I node from this, then this point will be IL max minus I node. This point will be IL minimum minus I node. So this will be my capacitor current. Now, what will be the nature of output voltage? So if you see from here, then this capacitor current is negative in entire duration of uh, on period, right? So, and this is constant. So if this constant current is being drawn from the capacitor, it means capacitor is continuously being discharged. It is continuously being discharged. And after that, during this off period, this capacitor current is positive. This capacitor current is positive. It means it is being charged. So, and this is a linear. So integration of linear will be further kind of parabolic function. So in this way, with this pattern, this will charge, right? Again, when next cycle on, this again discharge linearly. Like that, this capacitor voltage will vary. And if you see, this will be VC max, and this will be VC minimum, and this will be its average, which is V naught average, right? This is V naught average. So this is how this capacitor voltage varies in the, just I draw it with a red pen. This is how this capacitor voltage will have a ripple in the boost converter. Okay, now let us go to the next slide. Average inductor current. If I want to find the average inductor current, then this is our boost converter. This is the inductor currents we have seen. So previously we have taken the we have find out average inductor current by taking 1 upon T IL dt like that in the buck converter. The another way is also there. This inductor current here, this inductor current is same as input current, right? This is same as input current because it is connected to the input source. Now, if I see the what is the output power? So output power fee, I'm telling you the another way to analyze the converter. So the output power is P equal to V node I node, right? And V node is nothing but I node into R. So I can write I node equal to V node into V node upon R. So what is the power? V node square upon R or equal to V node I node. This is the output power. And what is the input power? Input power is nothing but Bs into Is. Bs or Vin into In or Vs into Is. That is equal to Vs equal to IL because the same current is flowing through the inductor. So we know input power and output power. And what is the losses here? Loss is not there because we have considered inductor to be ideal, capacitor to be ideal, switches to be ideal, so diode to be ideal. So there is no loss. It means whatever power is being drawn from the source, that will be supplied to the load. So both should be equal. So that same thing we have done. This is Vs into IL. This is Vs into IL. That should be equal to V naught square upon R. Input power should be equal to output power. Now what we have done? We have replaced V naught with Vs upon 1 minus d, which we have just arrived in the previous slide. Here, right? That we are putting. Now we have put it back here divided by R. So if we simplify it, this is Vs square upon 1 minus d square upon into R, right? So from here, one Vs will cancel out. So what is the IL? IL is equal to Vs upon 1 minus d square into r. So that is the one. Now you can replace this Vs with the V node, or in different forms you can get it. So this is V node square upon VSR. One Vs, if you multiply this with Vs and divide it by Vs, then this entire term is V node square upon Vs into R. So this is our inductor current. This is our inductor current, which you can further simplify like this. This IL, what is this? Vs upon 1 minus d. This is nothing but V node. So V node upon 1 minus d into R, right? And what is V node upon R? So we can write it like that. So V node upon R is I node. So that is 1 minus d. It means what is the relationship between, in morning someone was asking that can we consider output current always for the inductor? No, it's not like that. Now the relation between IL and I naught is in this fashion, right? So this is the relation between IL and I naught. So if I know the output voltage, I know the load resistance, I know now I naught. So with the help of duty cycle, I can find the average inductor current. And in morning we have seen that IL, because the shape remains same, so IL max is equal to IL plus del IL by 2, IL minus del IL by 2. Now, to find out del IL, what we can do, del IL can be find out from here. Here you can see del IL, either you use this magnitude or this magnitude. Any one will give you del IL, either this or magnitude of this. This is negative, so you just put V naught minus Vs, that will give you positive value. So that way we know del IL. So they have done same thing. IL, what is IL they have put? This Vs upon 1 minus d square upon R plus del IL. What is the del IL? Vs dt upon L, Vs dt upon L, and 2 will be there. So this is the value of IL minimum and IL maximum. Now we know that with the help of this IL minimum, once we know IL minimum, we can design the inductor, because for the critical condition or the boundary condition, this I minimum should be 0, right? This I minimum should be 0. In morning we have seen that this should be 0. That means the condition del IL equal to 2IL, that should be satisfied. So if it is 0, it means this term should be 0. This term should be 0, right? If this term is 0, then we simplified Vs upon 1 minus d square RL equal to Vs d upon 2L. T can be written as 1 upon F. So this is VSD upon 2LF. Now, if I find out the value, so VL will cancel out. So if I want to find out the value of LF, then this will be D 1 minus D square R upon 2. So if product of LF, that should be minimum, this one. Now, if we know the frequency, we fix the frequency. We discussed in fundamental of converters that this L into F, this provides basically the impedance, right? 2 pi F L. So if we increase the frequency, then L will be the less. If we have less frequency, then L should be the minimum. So F, let's say we know. So we put F to be down. So L minimum comes out to be this value. Now this is the value of inductance, which is just for boundary condition. If you put in the circuit boundary condition, if you put this L in the circuit, then you will get this kind of waveform. This is your 0 dt t. Then again will start. It will just touch and again start, touch, just again start, like that. But it will not go into DCM, it will not go into CCM, it will remain on boundary. But if you take the inductance L greater than L minimum, then it will always guarantee CCM. So for keeping the converter into continuous current conduction mode, we take it 5 to 10 times of L minimum, right? Or if we keep L less than the L minimum or L critical, then it will be definitely in DCM, because what will happen, energy will be released early only, and for the remaining time this inductor will not store the energy or not release the energy because it is already zero. It will start storing at this point only. So until that time it will wait for the switch to be turned on. Okay, now that way we design the inductor. Now if we want to find out the exact value of inductor for a given ripple current, then how to find? So this relation we already know, this relation del IL equal to Vs dt upon L. So from here L is equal to Vs dt upon del IL. That's what is written here, L equal to Vs dt upon del IL. So you know the input voltage, you know the duty cycle, you know the T or switching frequency, you will know. So if you are known with del IL, let's say you are given that 10% of XL or 20% of XL. So when you are designing for this equation, then what is the value of X? That is the 2. It means it is 200%. So ripple are 200% of the average current, and that is there. Yeah, this is the average current. This is the average current. So ripples are del IL by 2 down, del IL by 2 up. So 100% up, 100% down. 200% ripples are there. But if exactly 20%, 30% are given, then we find out the value of del IL from here. We put X equal to 0.3 for 30%. IL we know. We calculate this value, we put here, and we find the value of L. So this will give us this value of L. Then we need not to do it 5 times, 10 times. This will exactly give us the required value of inductor current ripple. Okay, so that is the way we calculate inductance. Now how to design capacitor? So let's again see this capacitor current waveform over here. So this is the capacitor current waveform, and as I have already discussed, this is the negative current during on period, this is the positive current during off period. So during this capacitor voltage will decrease, and during this capacitor voltage will charge, and this is del V naught. So we can choose any period, either this period or this period, but this period is easy to calculate, right? Area, and we already know this relation del Q equal to C del V. It means that if what is the small amount of charge which is accumulated when or which is accumulated or which is discharged when there is a change of voltage by del V. So if charge is increased, charge is capacity charged, and voltage will increase by amount del V. If capacitor is discharged by an amount of del Q, then what is the difference in the voltage or decrease in the voltage by amount del V? That is the that equation is telling. Now del Q, how to find? The area under the current curve, discharging current. So area under this curve. So what is the del Q from here? Because this is rectangular, simply rectangular. So both sides multiplication will give us the del Q. So this is I naught. So we are interested in just magnitude. So this is V naught upon R. This is I naught into this base. Base is time. So that is D into T. So from here, we get this del Q, and simply we make it equal to C into del V naught. Fine. Now from here, we find value of del V naught. So del V naught is equal to V naught dt upon RC. Okay, and T is equal to 1 upon F. So we can write this. From here we get the value of del V naught. So percentage ripple or VR or per unit ripple, output voltage ripple, that is del V naught upon V naught, that is equal to D upon RCF. So this formula gives us, if we know the duty cycle, we know the load resistance, we know the capacitance, we know the frequency, then we can find out how much ripple is present in the output voltage. In the reverse, if we know the value of ripple voltage, then we can find out the minimum required capacitance values from this formula. So both way we can find. So in this way we design the capacitor. Now one thing you must have observed in morning, this capacitor formula was C equal to 1 minus D upon 8 LCF square. 8 sorry it was 1 minus d upon 8L F square del V naught upon V naught. It was dependent upon L. Why? The buck converter is, having this kind of circuit at the load end. So this inductor will filter out lot of harmonics, right? And the remaining harmonics, because this inductor is directly connected to capacitor. So this value of L will filter out most of the harmonics, right? So if value of L you are taking more, then it will filter out more harmonics. And this is basically a low pass filter. Then capacitor will have less load over this. So the value of capacitance will be lesser if you have already taken L more, right? That's why this was coming into picture. But here what you see, this is the diode, and inductor is not this side. Inductor is filtering the input side current, not the output side current, right? So here C is just function of del V naught upon V naught only, not L, right? So more the ripple or the good ripple performance you want, more the value of C means. Performance means less ripple you want, more value of capacitance is required, right? So in this case, we will see if we design for the same ratings, then capacitance in this case will be more. Not only in this case, whatever converter configuration do you have, if inductor is not there, then the value of capacitor will be more, right? If inductor is connected or on the input side, then this current will be continuous. If inductor is current at load side, then this current will be continuous, load current will be continuous. And why it is happening, why capacitor value will be large required? Because when switch is off, that time inductor is no current is coming from source, only capacitor has to provide the energy during this entire period. Capacitor, sorry, when switch is on, diode is off, then only capacitor need to provide this entire energy. So capacitor stores that much energy that is required, right? That's why capacitor value is high. So this is the way we design this C. Now, if there is RC, one ESR is there in capacitor, then what will be the output voltage? This plus this voltage. Now, if this is the shape of current, then the voltage drop due to this ESR will be RC into this current, right? So same, this value to this value into RC, that will be added. So what will be the del V naught IR into this case? This del IC. Del IC is entire this to this, IC minimum to IC maximum, and into RC. So this component will be added when I compute the net ripple across output voltage. Then this will be del VC plus this del V naught ESR. So in order to, this much ripple, to compensate or to overcome this much ripple, I have to increase the capacitance value that is required. So this ESR, the importance of ESR in design of this capacitance becomes more important. Now let's go to this non-ideal boost converter. So what happens if non-idealities are added into the circuit? Does really performance of the converter deteriorates, or it remains same, or this non-ideality just simply of no use? Let us see here. So I'll not do all this analysis, just we will derive the boost converter output voltage. Okay, so this is boost converter, same boost converter. Let's say this is having one non-ideality RL in series with the inductance, that is the ESR of the inductance. So obviously this will be in every circuit. Now just switch is on. So switch is on, this will be the equivalent circuit when switch is on, right? So that is for T to DT period, and this is off from DT to T period. Now I'm just writing the inductor voltage equation, VL, when switch is on. So this is Vs. Earlier it was VL equal to Vs, but now this is RL is also there. So this will be minus RL into IL. this should be small IL, but I have taken a small ripple approximation. So this I'm writing just capital RL after SRA. Okay, after SRA, small ripple approximation after SRA. Okay, now if I say switch is off, then what is the VL? So this is the equivalent circuit when switch is off. So in normal case, it was Vs minus V node, but now it will be Vs minus RL IEL minus V node, right? So this is equation 1, this is equation 2. Now if I do the volt second balance, then this VL on into dt plus VL off into 1 minus dt, that should be 0. So Vs minus RL IL into dt plus Vs minus RL IL minus V node into 1 minus dt. That should be 0. Right? Let us simplify it. So T will cancel out. Okay, it will become equal to 0. So Vs minus RL into IL into D plus Vs minus RL IL into 1 minus D, that is equal to V naught into 1 minus D. So it is multiplied by D. This part will be common. So it becomes Vs minus RLIL D plus 1 minus D, that becomes 1. Okay. So that is equal to V naught 1 minus D. If you take RL to be 0 over here, then this term becomes 0 and it is Vs equal to V naught into 1 minus D. So V naught equal to Vs upon 1 minus D. That's the same equation. But if it is not the case, then this becomes IL RL upon 1 minus D. Right? RL equal to 0, it is same as previous equation. But this is not the case. Now let us simplify it. We know that for boost converter, we have a relation IL equal to I node upon 1 minus D or V node upon R 1 minus D. That is the relation, right? Let us put it back here in this equation. So in this equation, let's say, so Vs minus RL V node upon R 1 minus D. This equation equal to V node 1 minus D, right? We take Vs to be equal, we take V naught to be common. So this becomes RL upon 1 minus D into R plus 1 minus D. Okay. So from here, V naught becomes Vs upon, if I take 1 minus D to be common, then this is 1 plus RL upon R 1 minus D square. So if you put RL equal to 0, this is same relation as we had previously. But if you simplify this, so this is Vs 1 minus D upon R 1 minus D square plus RL. Now let us put D equal to 0 here. So what is the V output? If you put D equal to 0 over here, then this is Vs upon R plus RL. Let us put D equal to 1. So if you put D equal to 1 in this equation, then this is Vs into 0 upon 0 plus RL. So this becomes 0. It means that D equal to 1, output voltage is 0. But our ideal case says that at D equal to 1, this voltage should be infinite. But this non-ideal analysis says that at R D equal to 1, output voltage is 0, and that is a fact. That is a fact. And if you plot this equation at different value of RL, different value of non-idealities, then it will give you different output voltage at the same duty cycle. So let us see why it happens and how does it happen. So this is the curve you can see over here. If I say, so this is duty cycle versus gain. This is duty cycle versus gain. So gain is nothing but, like, if you say M equal to M is the gain, V naught upon Vs, you take this term to be here, so whatever left is the gain only. So in ideal case, this is 1 upon 1 minus t, 1 upon 1 minus t. So this is being plotted. So if RL is 0, RL is 0, it means ideal case, then your this output voltage gain that will increase with the duty cycle, and it is being shown over here that will keep on increasing. But if your RL is, if your RL is there existing, it is existing, then what will happen? Let me just a minute, just I am trying to zoom it for you people. Yeah, so if RL is increasing, then what is happening? This gain is increasing. At certain point this reaches to peak, then after that if you increase the duty cycle, then it is decreasing and it is reaching finally to 0 if you set duty cycle to 1. If RL is further, let's say this is 1%, if you keep it to be 2%, if you keep it to be 5%, for example, and if you keep it to be 10%, then this gain is decreasing, and the value of duty cycle at which this maximum value occurs, that also decreasing, right? So that is the practical case. And in general scenario also we say that people, how do they look like? Actually they are not same. जैसे दिखते हैं वैसे होते नहीं है. So same thing is here also, right? This converter is expected to deliver infinite gain, but it is not there. It depends upon the surroundings. It depends upon the known idealities present over there. More the known idealities, there is more constant on the gain. You can see here, if it is 10% about, then this gain of boost converter is just 1.5 times maximum. If it is 2%, then it can deliver up to 3-4 times only. If it is 1%, even 1% on non-ideality, it can deliver up to 5 times. It can boost the voltage up to 5 times. So it means what information we are getting from here, that the information we are getting from here is that we should make okay, we should do the proper analysis of the converter if we want to accurately know the performance of it, how does it behave when it operates practically. So that is the case. Now let us have an example. So we go to here. So the example I just to whatever we done so far, just to understand that only, that if let's say we are given a boost converter example, we have read so far the buck converter and boost converter. We are given one example. Design a boost converter that will have input voltage of 12 volt. So input voltage is 12 volt and the output voltage is 30 volt. Design it for CCM, continuous inductor current, and the output voltage ripple. So V input or Vs is given 12 volt, V output is given to 30 volt. Design for CCM such that the output voltage ripple V naught upon V naught, that is given 1%, less than 1%. So at least it should be 1%. The load resistance is 50 ohm. Also assume the components are ideal and take the switching frequency F to be 25 kilohertz. So these informations are given to us and we are asked to design the converter. Design the converter means we need to specifically design its L and C value. What is the L and C value? So if we know the formula directly, then we can put the values. If we do not know the formula, we can go from the fundamentals also. So both are correct way. So just in previous slides, we have derived the inductance value. What is the L minimum? This one, D into 1 minus D square R upon 2F. So L critical H D 1 minus D square R upon 2f. Remember, this value of L is applicable only for critical or critical inductance which is used for the CCM operation. It should not be used for DCM. Or this formula we know, whatever formula of output voltage we have derived so far, they are valid only for CCM operation. If our converter is operating in DCM, then we cannot derive or we cannot use this formula as it is. For the DCM operation, output voltage formulas are or the derivation itself takes in different manner. Okay, so let us put these values. So we do not know D so far, so we can find D from the output relation, which is V naught equal to Vs upon 1 minus D. So we need to find D from here. 1 minus D equal to Vs. So this is V naught minus D. V naught equal to Vs. So from here D is equal to V naught minus Vs upon V naught. Okay, so yes, okay, so this is 30 minus 12 upon 30, so uh, 0.6. Okay, 18 by 30, that is 0.6. So we know the duty cycle 0.6 into 0.6, that is the 1 minus D 0.4, and square is 0.16. R is given 50 and 2f is also given 20 kilohertz. So if you compute this, how much it comes? Can anyone of you please compute and let me know? So I will also come to know that you are there. What is the value of this? So 225, this 50.96 into 10 raised to power minus 3. Okay, so this is am I correct? Yeah. So this is 0.096. Okay, so it can be written 90 into 10 raised to power minus 6. Correct. So this is 96 microhenry, right? It is 96 microhenry. So this is the minimum inductance which keeps it on. Yes, thank you. That is correct only. 96 microhenry. Yeah, thank you who replied. So this is the L critical. Now at this value, it will be just on boundary condition, but we want to ensure that our converter should work always in CCM. So let us take any value, maybe 2 times, or maybe you can take 120 microhenry or 150 microhenry or maybe 200 microhenry, whatever available, which is slightly more than this, right? Similarly, C now we need to calculate. So C should be greater than, or C minimum should be D upon RF del V naught upon V naught. Okay, so D value is 0.6, R is 20, R is 50, F is 25 into 10 raised to power 3, and del V naught upon V naught, that is the ripple voltage, that is 1%. So we need to keep it in per unit here. Del V naught upon that is actually sometime we make this mistake. Del V naught upon V naught is 1%. So if I say this in per unit, so this is 0.01. So I will not keep 1 here. I have to keep it 0.01 over here, right? It's in per unit. So if you simplify it, then it gives us 48 microfarad. Yes, I think I am correct only. Purchase 48. Choice. Yes, 48 microfarad. So this is the minimum value of capacitance which ensure 1%. If you keep 48 microfarad, then it will give you exactly 1% ripple. But you are asked less than 1% ripple. It means you have to increase the capacitance value more than 48 microfarad. So let us choose, this is C minimum. Let us choose this capacitance to be nearest available is 100 microfarad, sorry, 100 microfarad in the market. So this is the 100 microfarad. So this is the capacitor value. What about the voltage? Because this capacitor is appearing across the load and the load is having how much? 30 volt. So capacitance has two parameters. One is I'm not talking from a numerical point of view. I'm talking just for experimental point of view. This we have calculated. Now we have to decide the voltage capacity of the capacitor. So here this is 30 volt at least required. So we can take this capacitor to be 50 volt or maybe 100 volt. So 100 microfarad, 100 volt. Similarly, when we are designing the inductor, so this is the value of inductance, that is okay, but we have to take care of the current also which is going through this. So we have to find what is the IL max which is flowing through this, IL plus del IL by 2. So that value we should know, and if we know that value, so definitely our wire which we are using for designing this inductor, so that should have capacity to carry more current than that. So that way we have to take care, we have to design the inductor. Remaining thing are switches and diodes. So that also we have to design. So whatever the maximum appearing voltage across this device, that we have to observe, and what is the maximum appearing current. So if we know these waveforms, then we can easily find out the, if let's say in this case, if I want to find the switch current, so switch current is nothing but when switch is operating. So this is the switch current only. This period is the switch current. So maximum value will be IL max. If I want to find the diode current, so what is the diode current? Diode current is this part only. So this part is diode current. Voltage waveform. So switch voltage waveform, when switch is on, in this period switch is on, then this is the 0, right? And when diode is on, then what is the voltage across the switch? So this is the voltage, this is the voltage across the switch. Here is your switch, right? So what is the voltage? We know. So this is switch voltage. Similarly, if you want to find the diode voltage, so when diode is, let's say this is diode voltage. So what is the voltage across the diode when switch is on? This is minus V naught, right? And when this is on, this is 0. So if I take this to be 0, this to be T, then this is the diode voltage. Okay. If I take this to be 0, this is to take this to be switch voltage. So what is the maximum voltage which is appearing across which is V node? What is the maximum voltage which is appearing across the diode? That is also V node. In that way, we can design diode voltage. Similarly, we can get the diode currents, IL maximum in both the cases. So now we know the ratings of diode, we know the ratings of switch, we know the current and voltages, current for the inductor current, we know the voltages, voltage for the capacitor and capacitance value. In this way, we can design the each component of a DC to DC converter, and this is common practice. This is the common thing which can be common concepts which can be used for any kind of DC to DC converter. Though due to because we have done detailed study, we have not covered all converters. That is not possible also in limited time. But yeah, concept we discussed, that remains true for all converters. Okay, so let us learn one more thing. This is buck converter. How to differentiate that which converter we should use at what time? This is boost converter. This is buck boost converter, right? So buck boost converter, we have not discussed analysis part. This analysis part remains same. You can try. If you face any difficulty, you let me know. I will personally help you. Okay, so what is the difference between these two? Obviously, here output voltage is less than input voltage. Here output voltage is less than greater than input voltage, and in this case output voltage may be, depending upon duty cycle, may be greater than input voltage, less than greater than input voltage, or maybe less than input voltage. Buck and boost, both operation are possible. So if you see inductance here, inductance, so in this case what is happening, that inductance is connected to the capacitance. So this capacitance, you can see the burden of the capacitance to filter out the ripples, that is lesser. So value of capacitance required here is lesser, and the output current, or you can say the load side current, that is continue. If you use, what is this R is just load only, right? So this definitely, these converters you will be using for certain applications, right? So you will replace those application, means this resistance with those loads. So in that load, the output current will be continuous, right? But what about input current? Here when switch is on, then only current is flowing. Switch is off, current is zero. So input current is discontinuous. Similarly, boost converter. In boost converter, what is happening? The input current is continuous because inductor is at this end. But what about the output current? The output current is discontinuous due to this diode, right? Output, when I'm saying output current discontinuous, that does not mean ki at this point it is always continuous. I just mean to say that if you remove this load, then this is not being supplied by the source. This is discontinuous, right? And due to this value of capacitance that becomes very large. Similarly, what is happening here in this case, this input current that is discontinuous, and output current that is also discontinuous. Output current is also discontinuous because inductor is not here. So in this case, both are discontinuous, but the advantage is that it can be used to lower the voltage and to step up the voltage. Both way it can be used. That is the advantage. But another disadvantage it brings along with this is that polarity is reversed. Polarity is reversed. So output voltage polarity is reversed and the input voltage polarity. That is the one more thing we need to take care in buck boost converter. So that way, depending upon application, what kind of things are required, whether we are using this converter for input side uh, performance improvement or output side performance improvement, or maybe for just buck boost operation like that. So these are the second order basic converters, and same analysis do follow for the uh, uh, other higher order converters as well. So we could not discuss this buck converter as well. So if next time we will start with the modeling only, and if any lecture is free due to any reason, then we will cover these converters if you say, otherwise you can do it on. So this, let's say this is not this converter we will later on decide. Just this is the another fourth order converters. One is converter, one is Zeta converter, one is Sappi converter. So in all these three cases, the output voltage is D upon 1 minus D, and these are called buck boost converters, similar to our conventional converter, buck boost converter. But the advantage of these are that they are having different advantages. So if I talk about the buck converter, let's say, then gain remains same, but here polarity is reversed. Polarity is opposite of input voltage. Time is up. I will take 2-3 minutes only. So second advantage here is that input current, that is continuous, because inductor L1 is connected to input and inductor L2 is connected to output. So this output current is also continuous. What happens in Zeta? Because these three belongs to same family. You can say they are three brothers. You know? So three siblings you can say. What about Zeta? In Zeta, the output polarity is same. Polarity is same. But input side, there is no inductor. This inductor now comes here. So the input current, that is discontinuous. But over the output current, this output current is continuous because inductance is connected along with this capacitor and load. So this is continuous. Now this is SAPIC converter. So in SAPIC converter, polarity is same. What about input current? Input current is continuous. What about output current? Output current is discontinuous because now inductor is not placed here. Inductor is current is placed over here. So whenever this diode is off, the source side is not connected to the load. So output current is discontinuous. So we see that out of these three, at a time, only two advantages are there in one converter, right? In first one, the polarity is the issue. In second one, input current is the issue. In third one, output current is the issue. So depending upon application, what is the priority, right? What kind of application is there? You know that these converters are basically used in power factor corrections. You must have read in research papers. So different type of topologies are used at different places, right? Zeta is also used, CUC is also used, XEP is also used, right? With some modifications also. Some they have their isolated versions also. So that way it depends upon application. So we stop here. We discussed a few important things. Few things has been not discussed due to time constraint. We'll see if it is it can be discussed later on. So if you have any doubt, please feel free to ask. Okay, so if you have any doubt, please ask. The value of LNC will be higher in which mode, CCM or DCM? Obviously CCM, right? So in morning we discussed in CCM, continuous current conduction mode, that was the requirement that inductance value is more, then CCM operation will be there. Any other questions, please? Please let me know if you have any other question. Okay, if no, then we conclude today's session over here, and we'll meet tomorrow morning with new exciting speakers and exciting topics. So I hope you have learned few things today, and this is second day only. We end the day 2 of our FDP. So thank you very much. Have a good day. We'll meet tomorrow. Thank you. Bye. Those who have not yet joined the Canvas, please take help of our team members and do join, because we will be having our first quiz on Friday. So before that, you should join the Canvas, and materials also we will collect and will try to upload as soon as possible. These recordings also will be available there. Thank you. Okay. If you enjoyed the sessions, you can share the feedbacks in our group so that people may be inspired to join and learn things. Thank you. Bye.